Good. Electric charge has one important property that was discovered by Robert Millikan. And what's this important property? It's important for you to know. Okay. He discovered that every electrically charged object has a quantized value with respect with he discovered that every electrically charged object, let's see, has a net charge that is quantized in terms of in terms of that value that we saw before, in terms of this charge, this value here, or this value, doesn't matter. Okay. In terms of the charge, oh no, of the electron slash proton, quantized in terms of the charge of the electron slash proton. So just a very smart experiment, very simple and smart experiment. And what does it mean exactly? In terms of that, we're going to denote it by E. That's called the fundamental charge. The fundamental charge. And what does it mean? Quantized. What does it mean, quantized, right? It's an integer number with respect to E. In other words, a given charged object may have a charge that is a 1E, 2E, 3E, 100E, and so on, but never a value in between integer numbers. Okay, in other words, it is not possible to find electrically charged objects. So an electric charge, you go to 1.5E, 100.1E, etc. That's not completely true, okay? But for the sake of this course, you can believe that. When we get into quantum mechanics, no, we know that is not exactly that. But for the sake of this course, it's fine to believe that. If we go here to Robert Millikan, let's take a look at Robert Millikan. Here you go, that's the guy. Robert Andrews Millikan. We have an entry in Wikipedia. We also have, he was born 1868. Okay, let's take a look at his biography. Okay, March was an American experimental physicist who won the Nobel Prize in Physics in 1923 for the measurement of the elementary charge. Not fundamental, but the elementary electric charge. Okay, and for his work on the photoelectric effect as well. Einstein, he won the Nobel Prize for the photoelectric effect too, right? And so did Robert Millikan. Okay, so it's elementary electric charge. Denoted by E is a fundamental physical constant defined as the electric charge carried by a single proton, or equivalently, the magnitude of the electric charge carried by a single electron. Let's take a look at his experiment. It's very nice to see how those guys. Today they sell those experiments out there. Today they sell those experiments, and we have the hardware at LA Harbor, that allows us to do this experiment, to repeat, right? The results, to repeat the experiment that Robert Millikan made, and find the same result that he found. And let me skip here. Let's see. Let's keep on playing.
Abra seu app no Mercado Livre e curta a série de filmes grátis.
Let's see. Let's skip
Sabe
that.
falar a frase?
I want to skip that.
Tá chovendo em inglês? Pensa aí. E você falou.
Here you go. Okay. Now here you go. What's the Millikan oil drop experiment? Okay. And it's actually, he used an oil drop, a bunch of oil drops to measure the electric charge of those drops. And he found that no matter how he would perform the experiment, he found that all those oil drops had an integer value of the elementary charge. Okay, let's play that.
Millikan's oil drop experiment. The charge of an electron was determined by Robert Millikan using Millikan's oil drop experiment.
Okay, let's take a look. Let's take a look here. Here's the oil, a cup with oil, right? And what he's doing here. One more student coming. Here you go. He is injecting those oil, you know, not the whole liquid, but just aerosol of oil here in this region, so you can have very small particles of oil in this volume. And by the way, this volume here is completely enclosed. It cannot be open like that, okay? And but that's a very nice way of illustrating it. And what else do we have here? We have here a battery, okay? A battery. This plate is negatively charged. This plate is positively charged. Okay, and when he turns on the battery, there will be an electric force between those two plates. They're going to attract each other, right? Because this plate is negatively charged and this plate is positively charged. But because those plates are fixed, right in place, they're not going to move towards each other. But the oil droplets that are being injecting here in this region will become electrically charged, will be electrically charged. There is a way of electrically charge those drops. Okay, and by adjusting the electric potential of this battery, he was able to apply a force to these droplets and even make the droplet fluctuate, become stopped at a single spot. Okay, just by adjusting the voltage of those two plates here of the battery. That's what he did. And he observed those droplets with a telescope, by the way, which is not shown here. Okay, and how did he put a charge to those oil droplets? He used X-rays at that time. At that time, he used X-rays. Today, we don't use X-rays. There is a better way of charging an object. We don't use oil droplets either, okay? Today, we use something else. Have you thought about performing this experiment with oil droplets? Would create a huge mess here inside, right? Nowadays, we replace the X-ray that was ionizing the oil droplets with something else. And we will replace also the oil droplet with some small beads that becomes electrically charged when they are, when we rub them. Okay, well, let's
The setup of Millikan's experiment shown consisted of two plates, which are positively charged plate and negatively charged plate. These two charged plates are in turn connected to a battery. An atomizer.
Atomizer, right? An atomizer, that's the right name for this device here. It's just like your regular spray. Okay, that's what the atomizer uses, the regular spray that we buy out there. But he atomized the oil.
Device used to emit liquid as fine spray along with microscope is arranged. The purpose of this microscope is to observe.
Well, he said it was a microscope. Some books call that a telescope instead of a microscope. Okay.
Observe the movement of tiny oil droplets. In the Millikan's experiment, with the help of an atomizer, a fine spray of oil droplet is sprayed into the upper chamber. It is observed that most of the tiny oil droplets spread all over the surface, while few oil droplets moving with certain velocity enter into the lower compartment under the influence of gravitational force.
Okay, so we have both the gravitational force acting in those oil droplets, but then we are going to have the electric force as well. The electric force as well that's going to be applied to those oil droplets. And don't forget, the Millikan himself was observing all those oil droplets with this device here on the spot, and he could adjust the voltage between those two plates to see if the oil droplets would hang out in space, right? Would fluctuate, would hover in that volume.
By observing the movement of tiny oil droplets, Millikan was able to calculate the mass of an electron. Now, X-rays from an experiment.
Oh yeah, here you go, X-rays as well to ionize the oil droplets. Remember, today we don't use X-rays, right? At that time, people were using X-rays all over the place, okay, until they discovered that X-rays was very dangerous.
Source are made to pass through tiny oil droplets. These energetic X-rays falling on oil droplets removes electron from the oil droplets and makes them ionize. The negatively charged electrons lost from the oil droplets due to ionization clings or gets attached to the oil droplets as shown, which makes these oil droplets negatively charged. The velocity of oil droplet could be controlled by changing the voltage across two plates. At high voltage, the negatively charged oil droplet tends to move upwards or rise towards the positively charged plate. This is because the electric force, which is the product of charge and electric field or oil droplet or QE, which is pointing upwards, is greater than the gravitational force mg acting in the downward direction. At a particular voltage, the oil droplets suspend in air. At this point, the weight of oil droplet, which is the product of mass and acceleration due to gravity, or mg, equals to the electrical force acting on the oil droplet, which is nothing but the product of charge and electric field, or QE. By moving ether to the other side of the equation, we get charge on oil droplet Q equivalent to mg divided by E. Millikan has found out that electrical charge on oil droplets was equal to the integral multiple values of negative 1.602 into 10 to the power 19 coulombs, that is Q equals to Ne. Here, Q refers to the charge, while N is the integer, which takes values 1 to 4. From this experiment, Robert Millikan has done.
Okay, he looks like he made a mistake here. This E here is supposed to be the lowercase e, okay? I like this video, but it looks like he made a mistake here. It's not to confound that with the electric field. It's actually the elementary charge.
That this fundamental unit of charge on one oil droplet, which equals to the value 1 into minus 1.602 into 10 to the power of minus 19 coulombs, or minus 1.602 into 10 to the power of 19 coulombs. This is nothing but the charge of electron. Using the charge of electron value of minus 1.602 into 10 to the power of minus 19 coulombs and J.J. Thomson's charge to mass ratio of electron, that is E by M value of 1.76 into 10 to the power of minus 11 coulombs per kg, Millikan has calculated the mass of electron. On substituting these values in the equation E divided by E by M, we get minus 1.602 into 10 to the power of minus 19 divided by the value 1.76 into 10 to the power of 11. This equation, on further calculation, the mass of electron was found to have a value of 9.11 into 10 to the power of minus 31 kilograms. It was also found that the mass of electron was about 1836 times
1800.
lighter than the mass of hydrogen atom.
Remember that I told you the mass of the electron is 1800 less than the mass of the proton? Okay, so it's not exactly 1800, 1836, but it's close enough to remember 1800, okay? And the mass of that's what the hydrogen atom is all about, right? The hydrogen atom is just a proton and an electron around it. So the mass of the hydrogen is approximately equal to the mass of the proton, okay? Because the mass of the electron is very tiny negligible compared to the mass of the proton.
As shown by the equation.
Okay, so that's the. Let us play this movie again. Let's see, how do I go? Skip it. No, it's not what I want. Well, let's just write it down here. And 1 minute. I'll do the following. I will keep it a link. I like this video.
Millikan's oil drop experiment.
Oh, yeah. Let's see here. Let's do it again. Okay, I will copy this link here and I put in my notes if you want to review it again. For a link illustrating Millikan's oil drop experiment, go to right in here, okay? And I'm just going to summarize the oil drop experiment, oil drop experiment. Okay, 1, 2 charged plates, 1 positive, 1 positively charged, and the other negatively charged. Okay. Oil. Atomizer. Okay. To atomize the oil, what does it do? Produces a mist of oil. 2 charged plates in an enclosure, inside an enclosure. 1 positively charged and the other negatively charged. Oil, atomizer. Okay. Those are the elements, and also there is a X-ray source. X-ray source, right? So what else? A telescope. The guy said the microscope. I don't agree with him. But let's put it telescope/microscope to observe the mist of oil. Those are the elements of the experiment, right? Elements of the experiment. See. And then we have the procedure. I'm gonna change here we go. Procedure. Spray oil inside this enclosure. Okay. It's possible to observe the oil droplets with the telescope. Okay. What else? Okay. Use X-ray source to ionize the oil droplets. Ionize the oil droplets. Don't forget X-ray is what we call X-rays are ionizing radiation. That's why it's called ionizing radiation. X-ray, gamma rays. There's someone that's gonna go into radiology, right? So you're going to work with that. Who's that? Who's gonna go into radiology? It's written right in here. That's Yorgo, right, Yorgo? You're gonna go into radiology, so you're gonna work with X-ray sources, right? And radiation sources as well, not just X-ray sources, but radiation sources as well. Ionizing radiation. Ionize the oil droplets, huh? Oh, there's one more element that I'm missing here, huh? Adjustable battery. By adjustable battery can change the voltage. That's not the right word. We usually use a power supply. The power supply is nothing but a battery that you can change. A battery that you can change the voltage, right? Change the voltage. So we have batteries that 1.5 volts. We have batteries that are 9 volts. The battery in your car is 12 volts. A power supply is a device that produces the same effect of a battery, but it's something that you can adjust. Okay, the voltage. Something that you can adjust the voltage. So it's one. Let's see how many elements. One. Oops. Yeah. Now I gotta wait for my not responding. Let's wait. Okay, good. My word here is stuck. Let's see if it's going to. Okay. Wow. Okay, let's see. Okay, good. Now we're back. So let's see how many elements we have. A, B, C, D, E, F, six components, right? We must have another one. Let's see. Yeah, I didn't put the enclosure, right? Enclosure. A, B, C, D, E, F, G, 7 elements to this experiment. The procedure, spray oil inside the enclosure. Okay? If you don't do nothing, don't do anything to the oil droplets, if you don't do anything to the oil droplets, they will just move downwards according to the force of gravity, right? And you can observe it, those oil droplets with the telescope. However, if you use the ionizing radiation, the droplets the droplets are going to become electrically charged. Use X-ray source to ionize the oil droplets. Oil droplets become electrically charged. And now that the oil droplets are electrically charged, you may see that they are going to be attracted towards one of the plates, right? Either they're going to be attracted towards one of the plates, or they're going to slow down their motion downwards, right? Their motion downwards is going to be slowed down, or they're going to float, depending on the amount of electric charge in the oil droplet, and depending on the voltage that you apply to those two plates that you saw. Okay, two charged plates. Depending on the voltage applied to the charged plates and the amount of electric charge in the oil droplet, okay, you will observe the following. You may observe the following, okay? One, for a given voltage, right? Let's see, depending on the voltage, let's see, for a given, let's put it this way. For a given voltage applied to the charged plates, okay, and the amount of electric charge in the oil droplet, you may observe one of the following. One, if the electric charge in the oil droplet is very low, okay, the oil droplet will move downwards, right? According to gravity, but at a lower acceleration value. At an acceleration a less than g. Okay, that's one extreme that he observed. Okay, that's one extreme that he observed. And by the way, that's an evacuated tube. Okay, that's the enclosure. You take out all the air from the enclosure. Otherwise, there will be some other effects there that would be difficult to calculate. Okay, on the other extreme, we have if the electric charge in the oil droplet is very high. I'm going to just copy this one here. You know, if the electric charge in the oil droplet is very low, it's very high, the oil droplet will move towards the positive plate, which to the upper move towards, not downward, would move upwards towards the positive plate. Because due to electric attraction, okay? And then he could see this droplet moving upward with the telescope, right? Now, if the electric charge in the oil droplet has a value, the oil droplet has a special value, right? Has a special value, it will has the right, not the special value, has the right value, right? The right value. It will be possible. It will be possible to see it hovering inside the volume, inside the enclosure. Okay, and it is those oil droplets that he used. It is these oil droplets that were used to calculate their electric charge. And he repeated this experiment several times. Most likely he hired a student to do that because it's lots of hard work, right, to do that. In this type of experiment, what does what do the scientists do, right? What does he do? Okay, initially he set up the experiment, he put everything together, make sure everything is working fine, perform the first experiment on his own, and then get a bunch of graduate and undergraduate students to repeat this experiment over and over and over again. Okay, and when he looks at the data, he comes to the conclusion that he doesn't observe any charge that's not an integer number of E. Okay, so that's a very important experiment. This experiment is so important that even today we perform it in the classroom, and we can even buy those things out there. We don't use oil droplets anymore. Okay, we use something else. We use some beads that can become electrically charged. And we do not use X-rays either. We use those beads that once they rub against each other, they become already electrically charged. That's the oil droplet experiment, Millikan's oil droplet experiment. Millikan's oil droplet experiment. Okay. It's a very, I'm gonna play that again. Let's play it again. Now I'm gonna play without any interruption, okay? And don't forget he made a little mistake there in his video, right? He put the capital E where he was supposed to put the lowercase e, right? The capital E is used to represent the electric field that we're gonna cover today, and the lowercase e is used to represent the elementary charge.
Millikan's oil drop experiment. The charge of an electron was determined by Robert Millikan using Millikan's oil drop experiment. The setup of Millikan's experiment shown consisted of two plates, which are positively charged plate and negatively charged plate. These two charged plates are in turn connected to a battery. An atomizer, a device used to emit liquid as fine spray, along with microscope, is arranged. The purpose of this microscope is to observe the movement of tiny oil droplets. In the Millikan's experiment, with the help of an atomizer, a fine spray of oil droplet is sprayed into the upper chamber. It is observed that most of the tiny oil droplets spread all over the surface, while few oil droplets moving with certain velocity enter into the lower compartment under the influence of gravitational force. By observing the movement of tiny oil droplets, Millikan was able to calculate the mass of an electron. Now, X-rays from an external source are made to pass through tiny oil droplets. These energetic X-rays falling on oil droplets removes electron from the oil droplets and makes them ionize. The negatively charged electrons lost from the oil droplets due to ionization clings or gets attached to the oil droplets as shown, which makes these oil droplets negatively charged. The velocity of oil droplet could be controlled by changing the voltage across two plates. At high voltage, the negatively charged oil droplet tends to move upwards or rise towards the positively charged plate. This is because the electric force, which is the product of charge and electric field for oil droplet or QE, which is pointing upwards, is greater than the gravitational force mg acting in the downward direction. At a particular voltage, the oil droplets suspend in air. At this point, the weight of oil droplet, which is the product of mass and acceleration due to gravity, or mg, equals to the electrical force acting on the oil droplet, which is nothing but the product of charge and electric field, or QE. By moving ether to the other side of the equation, we get charge on oil droplet Q equivalent to mg divided by E. Millikan has found out that electrical charge on oil droplets was equal to the integral multiple values of negative 1.602 into 10 to the power 19 coulombs. That is Q equals to Ne. Here, Q refers to the charge.
The mistake is right here, okay? This one is supposed to be lowercase e, which is this value right here.
While n is the integer which takes values 1 to 4. From this experiment, Robert Millikan has concluded that this fundamental unit of charge on one oil droplet, which equals to the value 1 into minus 1.602 into 10 to the power of minus 19 coulombs, or minus 1.602 into 10 to the power of 19 coulombs. This is nothing but the charge of electron. Using the charge of electron value of minus 1.602 into 10 to the power of minus 19 coulombs at J.J. Thomson's charge to mass ratio of electron, that is E by M value of 1.
Oh, that's what he's talking about. This is another experiment that J.J. Thomson performed, all right? J.J. Thomson discovered the electron, and he also performed an experiment that allowed him to find the charge to the mass ratio of the electron. He was not able to find those two separately, okay, J.J. Thomson. But Millikan was able to find E separately from M. And when Millikan's performed his experiment, which was completely different from J.J. Thomson experiments, he was able to verify this ratio here that J.J. Thomson found.
76 into 10 to the power of minus 11 coulombs per kg, Millikan has calculated the mass of electron. On substituting these values in the equation E divided by E by M, we get minus 1.602 into 10 to the power of minus 19 divided by the value 1.76 into 10 to the power of 11. This equation, on further calculation, the mass of electron was found to have a value of 9.11 into 10 to the power of minus 31 kilograms. It was also found that the mass of electron was about 1836 times lighter than the mass of hydrogen atom, as shown by the equation.
Okay.
Okay.
So let's close this one here. And that's what we have here, Millikan oil drop experiment. Look at carefully, there might be a question about this in the exam. It's a very simple experiment. It's not difficult to understand. It all it does, it involves electrical charges, right? And the Coulomb's law, as well. Okay. Let's electric charge, quantization of electric charge, experimental result obtained from Millikan's oil drop experiments. Charges can be either positive, negative, or neutral, right? But if you have a non-neutral electrical charge, it's going to have a integer value. So any charge, I'm going to write that down here. Any charged object will have an electric charge. We have the following electric charge. Insert equation. Go. There you go. The charge of the object Q is going to be N times E, where N is an integer number. 1, 2, 3, where N is an integer number. And E is the elementary charge. Elementary charge. The value is the value of the elementary charge, is the value of the elementary charge. Okay, someone is trying to come in. Okay, good. Now we have 10 students here. Okay, here I did one more student coming in. Nessa, okay, good. 9. So that's what we cover: electric charges, types of electric charges, quantization of electric charges, the electric force. That's what we cover. And good. What else you have to know? You have to know types of electric materials that we have out there. Okay, and there are 4 important types, but you have to remember only 2 types of electrical materials. But for the sake of this course, you have to worry only about 2. Okay, and those 2 are dielectric and conductors. Types of electric material. There are a total of 4 important electrical materials. But for the sake of this course, you have to worry only about 2. And, dielectric or electric insulators, okay? Or also called electric insulators. And conductor materials. Okay. Well, dielectric materials or electric insulators. Remember, dielectric materials, they are also called electric insulators. They prevent electric charges from moving freely inside them. So if you get a piece of a dielectric, and I have one here in my hand, this pen that I have here in my hand is a dielectric, is an electric insulator. If you put electric charges here in this material, electric charges are going to be confined only to a single spot. They don't move freely inside it. Okay? Plastic is one of them. Wood is a dielectric. Glass, pure water, acetone. Okay? All of those are examples of dielectrics, of electric insulator. Rubber. Okay, rubber. Have you ever seen, let me see if I can get, oh yeah, I have one here. Here you go. Have you ever seen this device, right? This device, this tool, right? This is a screwdriver. Okay. This one is a Phillips screwdriver. It's made of a metal here, and then you have a plastic handle. Okay, there's a reason why, here we have a conductor and here we have an insulator. There's a reason why the handle is an insulator. Okay. The reason we have an insulator here at the hand, you just handle from the insulator part. You don't handle from the metallic part, especially if you are working with high voltage. Okay, if you are working with high voltage, if there is any electric charge from here, you're not going to be electrocuted. Okay, so I have, for instance, a high voltage fence here around my property to prevent people from jumping the invading my property, right? So the voltage that this electric fence has is very high, around like 10 volts. So if someone tries to invade my property, they're going to receive a very strong electrical shock. But if I touch this, this screwdriver in the wires there of my electric fence, I'm not going to be electrocuted because I am electrically insulated by this handle. Okay? So dielectrics, that's an example of dielectrics. So what about electric conductors? Electric conductors is, are materials in which the electric charge moves freely inside the material. And metals are very good electrical conductors. Metals. Example, right? Example. Metals, ionized solutions, etc. Ionized solutions are what? Salt water, for instance, salt water, or any salt water would be NaCl, right? Salt water is NaCl. But then or any other salts, right? Any other salts, not necessarily NaCl. Salt is a very generic word for some other types of compounds, okay? Like potassium nitrate, for instance. Potassium nitrate. If you put potassium nitrate into water, you're going to come up with a ionized solution, etc. Okay? Those are examples of conducting substances. Let's see if I can have a drawing. Let's see if I have a drawing here to show you. That's the illustration for the Coulomb's force, right? That you saw before. Here's the x-axis. Okay, and now we have 3 electric charges, and we are trying to find the net force in this electric charge right here. You see that? We're going to have this force here due to this negative charge, and this other force due to this positive charge that's going to be repulsive. Okay, and that would be the net charge, more or less. Okay, and here's another example of 3 charges distributed in the 2-dimensional space. The previous example was just for 1-dimensional distribution of charges. And we want to find out the net force in the charge 1. Okay, like that. One is going to be attractive, other one is going to be repulsive, and we get this net force according to the principle of superposition, just like we got for the gravitational force. Okay, here's the theta angle. Okay, I'm making it a little bit larger in this drawing. Okay, here's another case in which the charge has moved away from the y-axis. You can see that the force changes as well, right? And those are examples of the electric force. That's 9:46 right now. Let's see here. Let me see if I have another illustration for you. Yeah, okay, right. Yeah, okay, I don't have any illustrations on electrical. Let's see if your book has. And by the way, I have posted the homework there. Copy right here. Wiley resources. Launch. Okay. Here you go. Here's an ebonite rod. This is an insulator, right? This is an insulating material that can become electrically charged. If I rub the ebonite rod with this animal fur, one is going to become negatively charged and the other is going to become positively charged. Electric charge must conserve. So that's one example of a dielectric material. Here's another example of the Coulomb's force, right? This one here is electronic ink. I'm not going to cover that, but it's electronic ink. Yeah, electronic ink. You use Coulomb's law to print stuff, right? Conductors and insulators. Okay. And electric charge can not only exist on an object, but it can also move through an object. However, materials differ vastly in their ability to allow electric charge to move or to be conducted through them. To help illustrate such a difference in conductivity, he calls the conduction of heat. Okay, the electrical conduction is very, objects that conduct heat. They're also very good electrical conductors. Okay, that's the comparison he's making out here. So a metal object, if you are holding a metal object touch a metal object for a very high temperature, you're going to feel the heat on the other side because the metal conducts heat very easily, but it also conducts electrical electrons as well. Okay. Similarly, an electric insulator ends up being also a very good heat insulator, thermal insulator as well. Okay, that's no coincidence. There's no coincidence because heat is carried by electrons in a metal. Heat is carried by electrons in a metal. Okay. So that's the part here that we just talked about, and it's 9:49 right now. Let's take attendance. Okay, lab attendance. Let's see here. I'm going to copy this one. Lecture attendance, create. Okay. And I don't need this one. Delete. Yeah. I need this one here. That's going to be my lab attendance. Lab attendance, and it's going to be first. I'm going to sum 2 days, right? So this one here. And now we get I'll copy that and paste it here. Good, and now I can delete it. This one was last time attendance. Let's clear this one. Why do I have one here for Scalera? Let's see. Okay. Total. Yeah, I don't know why I have one there, but now here you go. Jacqueline, are you there?
Yes, I'm here.
Thank you. Alexandra Barreto. Are you there, Alexandra? Okay, I'm gonna put a little star here on Alexandra's name. She's here, but it looks like she's away from the computer. Next is Sky. Are you there, Sky?
Here.
Thank you. Vanessa.
Here.
Thank you, Vanessa. Habi. Habi Hain. I don't see Habi here. Okay, Ashley. Hi, thank you, Ashley. Corina.
Here.
Thank you, Corina. Norberto Lopez.
Oh, I'm here.
Thank you, Norberto. Vanessa Mena.
Here.
Thank you, Yorgo.
Here.
Thank you. And Paul Zapata.
Here.
Thank you, Paul. And we have one more student here, right? That was not in my list. Is that Lisel?
Yeah, I just added this class recently.
Oh, you just added. Okay, so let
Yeah.
me add the name here. And then I will look at my, let's see, Lisa, is that your last name is, your family name is Vince or Cruz? Which one's your family name?
It's Vince Cruz. Like
Cruz,
it's
right?
two. Yeah.
Like that?
Yeah.
So, okay, thank you for joining us. And we have 9 here. Is only Alexandra, right? Alexandra is here. Oh, wait a minute. We were supposed to have 11. Is there any other student here that I didn't call? Let's see. 10. Yeah, it looks like we have one more student that I didn't call. Let's see.
Professor, did you call my name?
Yeah, who is that? Alexandra?
Alexandra?
Yeah, I called you. Okay, good. Thank you. And now you have attendance here. Let's see. Ashley, Corina Jurado. Okay. Jacqueline Arieta. Yeah, Jacqueline is there. Vince Cruz. Norberto Lopez. Okay. Paul Zapata. Sky Carvajal. Vanessa Scalera. Vanessa Mena. Yeah. Oh, strange. Let's see. It says 10 here. Okay. That's the reason. Okay, now we have everything fine here. 9:55. So let's go for our break, right?
Professor, I was also gonna ask, because in the beginning I was hard time getting in. In the Zooms, the links aren't there. I had to go back to the email they had sent to join. The Zooms, there's no links in there to join this class. I'm in the Zooms.
Let me see. Are you talking about the Canvas or where are you getting the link?
No, I'm talking, yeah, Canvas, where you go to Zoom to like get in the class.
Oh, yes. I know what you mean. Okay, sorry for the confusion. That's right, Yorgo. You have, I'm not using the Zoom from the college. I'm not using the Zoom from Canvas. I'm using my own personal Zoom. Okay, that's why you cannot get, but if you go to the syllabus, right, and click this link here, then you can get into the classroom. Okay.
Oh, okay.
So you have to use this link here. Why you have to use this link here? Because I'm using my own personal Zoom. Okay, and yes, there is a Zoom link in Canvas, but that Zoom account I'm not using. Okay, that's the reason. Okay, so 9:56. Anybody else? Any questions? Break. Okay, so break from 9:56 to 10:11. 10:11 a.m. Okay, so see you in 15 minutes. Okay, I'm back here. What I'm going to do, I'm going to continue lecturing here for maybe another hour. And then we use the remaining time to set up the groups. And we're not going to have any specific lab today, it's just for set up the groups, okay? Then the actual lab is going to be next week, lab between quotes, right? It's not exactly lab. And what I want, let's see, am I sharing the screen? Not yet. Here you go. So here you go. I plan just to set up the lab groups. And then we do the actual lab activity next Wednesday. So,
Professor, are we doing it in class or do we have to do by ourselves with the group?
in class, I have, you're going to see how it goes. I'm going to provide you with a spreadsheet. I'm going to explain how the lab is done in actual life, in real life, okay? And during those, during the lab meeting, you do some activities with the spreadsheet, you're going to analyze data, things like that. And you do that in group. You're gonna have some of your classmates as your group member, you can talk to them and finish the lab activity, okay? So let's talk about something else that was mentioned in that video that you saw. That is what we call electric charge, right? Which is a property of matter. By the same token that mass is a property of matter as well. That is electric force, okay? Which is force between charges. And that is something else, and that's what you're gonna cover now. Electric field, okay? And that's what we're gonna cover right now. This one belongs there at the top. Remember that I told you that there are 4 types of materials, right? Let's see. Let's put it here, another one, electrical materials, right? 2 types of electrical materials, and then now we have this idea that's called electric field. And what are the other 2 types? There's a total of 4, right? The total of 4 electrical materials, but there are 2 other that are important too, but we're not going to cover in this course, are the semiconductors and the superconductors. Okay, let me just electric materials, conductors. Let's start like that. Dielectric first, conductors. And then, I'm going to put semiconductors here. Okay, and then we have what? The superconductors. But like I said, we are going to concentrate only on those ones right here. And now we can start talking about the electric force, the electric field. what is the electric field. First, I'm going to give you a qualitative idea what the electric field is, but I can tell you that the mechanical counterpart of the E field, the electric field, is the acceleration of gravity. Okay. So now you have the mechanical counterpart, and then you can start understanding what this electric field is all about. The idea of electric field was something that took me a while to understand when I was an undergraduate student. Took me, and most likely you're gonna have, you're gonna have difficulties understanding, but that's normal. That's part of the learning process, right? So, but if you can start thinking about the electric field as the mechanical counterpart, let's see, if you, let's put it this way. The mechanical counterpart of the electric field is the acceleration of gravity, okay? You can start thinking about that. And let me, whatever steps I show you right now can also be used for the acceleration of gravity as well, okay? So here you go. We have this charge right here in space. Let us come up with the X and Y axis of this electric charge. Okay. Let me move this one a little bit down. Let's see. A little bit more. Hopefully I didn't. Oh, yeah, it looks like I managed to do it. Right? X and Y axis, charge Q1, they're at the very origin of the XY axis. You already know that if you have another charge nearby it interacting with this charge, there will be a repulsive force applied to charge 1. Okay, I named it, it's not supposed to be Q1, it's supposed to be QT. Okay, there's a reason why I call it QT. I call it a T for test charge. I'm performing an experiment, a thought experiment. Okay, and see, and now that you have this force, that's clear to you because you already saw the idea of the Coulomb's force. There is a distance between the main charge and that test charge. The distance, the vector position is this one that you see. Vector position from 1 to T, right? From the charge 1 to the test charge T. Here you go. Here's the vector position again. If we get rid of this test charge, it's supposed to be Q, lowercase q. If we get rid of this test charge, now there is no force whatsoever, right? While the test charge was in there, there was a force. But once we get rid of this test charge, notice that I made the test charge just like a ghost. Let's see if I can get it better so you can see it. Format, shape, size, and position. Doesn't look like I can do any better than that. Okay, I'm gonna leave this way, otherwise it's gonna take too long for me to put it the way I want it. Okay. Yeah, so no force whatsoever. If once I get rid of the charge, right? That's why I put a dash around it. Although there is no force at that position, there is something else left behind when I remove the charge. There's something else that I call the electric field, but the ability of this charge to exert a force at any point in space. Okay? The idea of the gravitational acceleration is the same. Okay? We can repeat the same thought experiment for two masses, right? And then you're going to conclude that there is something that we call the acceleration of gravity, which is in reality the gravitational field. That's what the acceleration of gravity is all about. With one important difference, there is no negative mass. There is only positive mass, right? And the positive masses, they exert an attractive force between them, not a repulsive force like it happens to charges of same sign. Okay? And now if I want to map the electric field around this other charge, I can do that by placing the test charge that you saw before in another spot, right in here. See that? We have the electric force there being applied. I remove the second charge, and what's left behind is the electric field, the ability of the main charge to apply a force in space. And here's my test charge in another spot. Okay, I'm mapping the electric field around this point charge. And now I have electric field 1, electric field 2, electric field 3, and so on surrounding this guy. Okay? If I were to repeat for the masses, right? Let me repeat that for the masses. And I will, but instead of a charge, it's going to be mass in place, right? So here is not going to be Q, it's going to be M1, and I'm going to take out this positive. Suppose that we have a planet now, planet of mass M1, right? This planet of mass M1 we place it along an x-axis. Not just an x-axis, but a y-axis as well. Playing the movie here for you, right? Here you go. I don't need that anymore. And now what I'm going to do next, I'm going to put a test mass, not a test charge, but now it's going to put a test mass right in here. And I'm going to label it test mass, M sub T. M sub T. The difference being that the force is not going to be repulsive. The force is going to be attractive, right? But first, let's put the vector position there, right? And then I can erase my vector position, otherwise my drawings are going to become too busy. Here you go, that's the vector position. Vector position from the mass 1 to the mass T, right? Has to, the end of the vector position has to be at the center of mass T. I can go a little bit further away, around here. Okay. And what else? Now I don't need this vector position. Let me erase it from here. And then what we get? We are going to get a force, but it's not going to be a repulsive force. It's going to be an attractive force because we are dealing with the gravitational force. And then I'm going to change the direction of, maybe it's this one. Yeah, that's the one. Change the direction of this force, right? Force of 1, apply it to the test mass. I don't need that. Let's see if I can put my vector position back there. Just to document, here you go. Yeah. Should be easy, right? I'll take it out. Copy this one. And paste. I don't need that anymore. I don't need that either. This is the vector position, right? The moment I remove this test mass, right? And I am denoting them by making it look like a ghost. The force is no longer there. The force becomes 0. Okay, the force becomes 0. I don't have m sub t there anymore. Right? The force becomes 0. But something else is left behind. And this something else see here. Something else is left behind, and I'm gonna get this vector, and this something else I'm gonna draw with a different color, so you know it's a different quantity. This something else is not a force, it's the gravitational field or the gravitational acceleration. So that is the and I'm gonna put it in red color as well. The gravitational acceleration, which is also called the gravitational field, which is also the gravitational acceleration, okay? And you can do that for all points around this mass. And you're going to map the gravitational field of this mass by the same token that we manage to map the electrical field around my point charge. Okay. Going back to our electric field. Going back to our electric field, the electric field is going to be stronger the closer you are to your source of electric field. See that the length of this vector is shorter than the length of this vector, right? Here is the gravitational field nearby the surface of the Earth, right? Nearby the surface of the Earth. The gravitational field looks like it is uniform, but it's not uniform. It's uniform only up to a certain point. As we climb higher and higher in the atmosphere, the gravitational field becomes smaller and smaller. Okay, and by the same token that we have a uniform gravitational field, we can also have a uniform electric field. Okay, and that's where, and that's when, you know, we were performing that Millikan's oil drop experiment. That's where the uniform electric field comes along. When you have two big plates next to each other, one positive and the other negative, they produce this uniform electric field. They produce something like that. And working with something that's uniform is easier, mathematically speaking. Okay? So let's get it here, Coulomb's law. Okay, so let's write that down here. Electric field is, we can define the electric field. We can define the electric field as the ability of an electric charge to exert a force in another charge, even when we don't have a charge in a specific spot, okay? It is possible to map the electric field of a given electric charge by placing a small test charge nearby another charge. A small test charge, and this small test charge, we call it Q sub T. It has to be small because it cannot affect the electric field nearby it. That's why we say a small test charge. Oh, by the way, that's also negative. That is also a small test charge. That's also positive. Nearby another larger charge. The test charge always has to be positive. Another larger charge, and that we call Q1. Okay, it's possible to map the electric field of a given electric charge Q1, okay? By doing the following. One, placing, I don't like it. This guy is, let's see, move it. Here you go. One, placing a small test charge. Not nearby, but at a given distance. A small positive test charge at a given distance from Q1. Okay. 2, determining the direction and intensity of the electric force applied to QT, right? 3, removing the test charge from this position. And 4, recognizing that the electric field will have the same direction as the electric force when the test charge was in place, like that. What else? It's not just that, right? Repeat steps 1 through 4 for different positions. Okay? I'm just documenting what I did there in the drawing, right? That's how we map the electric field around another electric charge. Okay. So here you go. Let's see if I have, okay. Think about drawing all the electric fields. Here you go. Think about drawing all the electric field in terms of a bunch of arrows around the test charge, okay? Think about that. It's lots of work, okay? draw a little arrow here, another arrow here that's longer, and so on, right? It's lots of work to do that by hand. For this reason, because of this, this amount of work that people figure out a different way of representing the electric fields around a charge, okay? This is the vector representation of the electric field. Vectorial representation of the electric field. I'm going to even write it down here. Vectorial representation of the electric field. Oops. Symbol times area. Okay. Vectorial representation of the electric field. Okay. So there is another way of representing the electric field that's much easier to draw. Requires much less work. Okay, so I can write it down here. And by the way, I'm going to transfer here this. Oh my goodness, again, I didn't want that to happen. You gotta be careful about not clicking. Now it's gonna take forever to get out of this mode. Wait. I can access this guy here, but I cannot access this one here. Oh my goodness. Okay. It looks like, okay, good. This one here, I want to put elsewhere because it belongs to Coulomb's law, okay? Those two are an example. Those two examples that you saw before, that should go before electric field, before electrical materials. Electric material, okay. Electric charge, I'll put it here. Example of electric force. Okay. This example is 3 charges lined up, just like you saw before. Okay, and he's choosing the other one. Let me just show you so it's easier for you to remember. Let's see here. That's electric field. Must be, yeah, it's another one. Illustrations. Electric charge. Okay, so here you go. That example that you see is this problem here, is this illustration here that you have. 3 charges lined up, and you want to find out the net force on charge number 1, okay? That's what you see in there. And the other example is this one here. The charge is disposed in a right angle triangle, distance A here, distance B here, and how you solve the problem. Okay, going back, right? Example 1, example 2. Let's put example 2 here. Example 1, right angle triangle. Example 1, lined up. Example 2. Electric field. This one, the example. Okay, so let's see here what's going on here. That's week number 2. Okay, I was here. Okay, so here you go. There are 2 ways of representing the electric field. One, the vectorial representation, and 2, the electric field lines. The electric field lines. There are 2 ways of representing / visualizing the electric field. The vectorial representation and the electric field lines. This one here is less work. Less work compared to the other. Okay? So let's take a look. Let's see this one that I want. Right? See that? We are representing the electric field around this charge. It's lots of work to draw different arrows, a bunch of different arrows around it. And then you also have to measure the arrow. The arrow here is longer than this one because the electric field is closer to this charge. And for this reason, it's more intense. Okay? But in order to cut down the amount of work, we scientists, we figure out another way of representing the electric field. Not just the electric field, but also the gravitational field. By using electric field lines, okay? For the case of the point charge, the electric field lines are going to be something radial that behaves, that points away from the main charge. Okay? It's much easier to draw something like that, far less work to draw something like that than to draw the vector fields. Okay? Those lines are representing the direction of the electric field. We say that the positive charges are sources of electric field. Why is that a source of electric field? Because the electric field radiates from the charge. Radiates away from the charge. Okay. And what else? This guy here encodes the direction of the electric field, but it also encodes the intensity of the electric field. Okay, and where is it encoded? Where the intensity of the electric field is encoded here? The intensity of the electric field is encoded right here in the distances between the electric field lines. In this point here is in this region here, those electric field lines are much closer than in this region here. See that? What does it mean? It means that the electric field right here in this region is stronger than the electric field right here in this region. So we have a concentration, a higher concentration of electric field lines here in this region compared to this region. Okay? So we can have an idea not just of the direction of the electric field, but also the intensity of the electric field. If it is a negative charge, the electric fields point towards the negative charge. We say that the negative charges are sinks of electric fields. Look at the vectorial representation. The vectorial representation would be something like that. Okay? Vectorial representation would be something like that. And I put only 3 vectors there. In order to have a better idea, I have to put far more vectors than that. Whereas for the electric field lines, it's far easier, far less work than the other one, and still carry the same information, okay? This is just the qualitative idea of electric fields. This is just the qualitative idea of electric fields And the quantitative idea, we have to use the concept of the Coulomb's law, okay? And that's where the mathematical definition of electric field comes along. But first, let's document vectorial representation and electric field lines representation. Okay. In the vectorial representation of the E field, we have both the direction of the field and its intensity represented by the length of the vector. In the electric field lines, E field lines representation, we also both the direction of the field and its intensity are all the direction and intensity of the field are also encoded in the following way, right? One, the direction of the lines of the arrows, the direction of the arrows, and the distance, the relative distance between lines, the relative distance between lines at a specific region around the main charge. The higher the density of lines in one region, the more intense the electric field. Okay? Vectorial representation. E field lines representation. Direction. The direction and intensity of the field are encoded in the following way, right? The direction of the arrows represent the direction of the field, represent the direction of the field, and the relative distance between lines and a specific region along the main charge represent the intensity of the field. The higher the density of lines in one region, the more intense the electric field. Okay? But then we can start talking about this is the qualitative, right? Qualitative representation. There are two ways of representing, visualizing qualitatively, qualitatively, right? The electric field. Quantitatively, the electric field is defined by a formula, okay? An equation, right? Let us start with Coulomb's law, remember? The field is related to the force. And I'm going to get this one here. I'm gonna get this one right in here. Consider two charges, 1 and 2. We want to find the electric field of charge 1. Okay, how do we do that? We do that by starting with the equation for the electric force, with the equation for the electric force. Okay. When we remove Q2, we don't remove, okay, exactly remove. When we remove Q2 from the right side of the equation, okay, I put remove between quotes. We get the equation for the electric field. How do we do that? How do we do that? I don't remove it completely. What I do, I just pass Q2 to the other side of the equation. Okay. And now that I no longer have Q2 here on this side, I change my notation by just referring to the charge number 1. See that? Here's the charge number 1. Here's the distance from the charge number 1. And here's the vector position from the charge 1. This ratio that you see here, we define as the electric field. Is the ratio, and we also remove the electric field of charge 1. Okay, and we no longer need the Q2 charge in there. That's how we define mathematically the electric field. We go, remove it. Electric field expression of the electric field of a point charge. Okay, it's no different from the gravitational acceleration, right? It's no different from the gravitational acceleration. So the force, and I'm gonna use this equation here. Recall the gravitational force between two masses. Okay, mass 1 and 2. Mass 1 and 2. The force applied to 1, the force of 2 in 1 is going to be given by big G, but now we have a negative sign here. Okay, I'm doing the vector notation. Mass of 1, mass of 2, divided by the distance between 1 and 2 in the direction that goes from 2 to 1. Okay, force that 2 applies to 1, right? If I want to know the acceleration of gravity due to mass 1 alone, right? What I have to do, I have to pass M2 to the other side, right? And what we end up getting here, you know, is going to be, we have to remove, we have to adjust our notation to state as just the genetic distance from mass 1, and this ratio that you see right in here becomes nothing but the acceleration of gravity or the gravitational field of mass 1. Okay. Another way to do that, right, is another way. Here's the acceleration of gravity, or the gravitational field of 1. Another way of doing that, maybe you're far more familiar with that. Another way of doing that is by recognizing that M2, that the weight of M2 is, right, at a given spot, the weight of M2 at a given spot is what? It's going to be M2, let's see here, M2G. Okay, but let's not forget the G is the mass number 1. And then we go back here to this equation. Okay, I'm going to put the M2 right in here in front of. I'm going to put the big G here in the denominator, in the numerator, sorry. And now I recognize that this term here with the negative sign is going to be the acceleration of gravity. And let's not forget, is the distance from mass number 1, unity vector position from mass number 1. Okay, this M2 cancels out with this M2, right? That's another way of doing the same thing. And we end up, do we get the same equation or not? We do, right? Negative, G, big G, right? Big M1, R1 is square, R hat 1, R hat 1. Okay? That's another way of doing that. And now we are coming to a point where we can have our break again. Any questions about that? Notice that both for the gravitational field and the electric field, their strength goes down with the inverse of the square of the distance. Both cases. The strength is proportional to the charge, okay, which is the source of the electric field. Here, the strength of the gravitational field is proportional to the mass, to the main mass that we have. Okay, so Q1 and M1 are the sources of the electric and gravitational fields, respectively. Okay, so we are coming to a point where we're gonna have a break, and now, yeah, when you come back, I will separate you into groups. 11 o'clock. Any questions before we go into the break? Okay, so break again from 11 to 11:15. Break from 11 a.m. to 11:50 a.m. So I see you in 15 minutes. Okay, I'm back here. And let's see, let's get to the groups, right, I mentioned to you. That's the material I want to cover about the electric field next time, That's what I want to cover for the electric field today. Next time, we will do some examples. But now I want to create groups of students. Okay, lab groups. Lab groups. Groups of students that will be used for the rest of the semester. Okay, and what else I'm gonna do? I'm gonna give you, let's see. First step, first separate you into groups. Next step, I will create a group folder that only your group members will have access. Okay, that's what I'm gonna do now. No experiment today. For today, just setting up the groups, okay? And let's start with whoever is at the top here of the attendance. I'm gonna put it here. Let's see, group one, group number. I want to do, looks like we have 12 students, right? Right now we have only 8. Hopefully the other 4 are gonna join us next time. I want to start with Jacqueline. Hello, Jacqueline. Let's see. Are you there? Yeah. Do you already know any other student that would like to have in your group, Jacqueline? We know any student you do? Okay, who is that? A student that you'd like to be in your group, right? Who would that be? Yorgo and Paul? Okay, good. So Yorgo, let's see. Yorgo is here. And Paul, okay, Paul Zapata, right? Okay, here you go. You 3 are group number 1. Okay. So start sharing contact information among each other. And you can do that through Canvas. Now let's talk with Alexandra. Hi, Alexandra. Are you there? I don't see Alexandra here. Okay, so I'm going to skip Alexandra. Looks like she left. I'm going to give her half a point for attendance, okay? And we still do not know Sky. Hello, Sky. Sky was here before. Looks like she left, unfortunately. Okay, let's give her half. Vanessa. Vanessa is here. Like Vanessa? Okay, good. Do you already know any other student that would like to be in your group, Vanessa? You don't know anyone? Okay. So I'll put you in group number 2, and then as we go along, I will ask the other students to join the group with you, okay? So Habi is not here. Ashley, are you there? Yes, okay, good. You wanna join the group with Vanessa, or Ashley, or you have someone else that you have in mind? Sky and Corina. Okay, Sky left, right? Okay, so I'm gonna put you in group number 3. Corina, okay. So hopefully, let's see, Sky. Yeah, okay. Okay, Sky and Corina, good. So we'll just contact Sky that she's in your group. Okay, and now let's see, Norberto. Do we have a group, Norberto? Let's see if Norberto is here. Yes, with Vanessa Mena. Okay. Oh, Vanessa Mena. Okay, there are two Vanessas here, right? So I'm gonna put you in group. Would you like Vanessa or the other Vanessa to join your group too? Right now she doesn't have any group, right? What about, sure, okay, let's do that, Vanessa. The two Vanessas, right? Vanessa Escalera, Norberto Lopez, oops, and Vanessa Mena, group number 2. Okay. And now we have Lizelle. Let's see. Pose already has a group. Let's see here. We have how many? So do you know any of the students here in the classroom, Lizelle? Let's see if she's here. Lizelle, yep. I'll join whoever wants to take me. I don't know, you don't know anyone? Okay. So you have the choice of 3 groups, group 1, 2, or 3, okay? It's okay to have one group is 4 students. And there's still Alessandra and Habi, right? If they show up, you know, for now, I will put one of those 3 groups. But then if a Habi or Alexander shows up, I will transfer to their group. Let's do it this way. Okay, for now, you just join there. This either, you know, one of the 3 groups, right? So what about, well, what about join group number 1? Is that okay? Jacqueline, Yorgo, and Paul, would you welcome Lizelle to your group? Okay, good. So I put it here, number 1, you start exchanging contact information. Okay, Habi didn't show up. Alexandra disappeared, unfortunately. Okay, so now we have all the groups, and I will sort this list by group number. So it's easier for me to manage. For now, group 1 has 40 students, and I have to create a group folder for you in my Google Drive. Okay. And let's go there. You know, send your message in the okay. Good. So let's go to my Google Drive here. Go to Drive. I have been using the Google Drive for my students since 2005, since 2001. I guess I've been using that since 2009, maybe. It's been a long time I have been using it. It's working very well. Maybe there's a better way of doing that in Canvas. I still didn't figure that out. If there is, you know, if I figure that out and I discover that's better, I will transfer to Canvas. But for now, let's see. I gotta create. I don't need that anymore. Why keep on move to trash? I don't want that. Now let's see. Modify it. People type. How do I get to create? Let's see. Okay, I'm going to do the following. I'm going to change this one. Let me transfer this thing elsewhere. Good. Now I can. New folder. 2024. New folder. That's going to be group number 1. Create. Group number 2. Group number 2. Group number 3. 1, 2, 3. And I will share a link for this group. Let's see, restricted. Anyone with the link can edit. Okay. Anyone with the link can edit. Copy link, and I'm going to send this link to Jacqueline. Okay, Jacqueline, and then you share this link with everybody else. Okay. So the way it is, the group members of group 1 will have the link for group 1. Okay. Don't share that link with anybody else outside your group. And I will send this link via chat here. Chat. Okay, here you go. I'll send that to you right now, Jacqueline. Okay, share that with your other group members. Your other group members are Yorgo, Lizelle, and Paul. And now let's go for group number 2. I will share this link. Restrict anyone with the link, viewer, edit. Copy the link, and that's going to be, let's see, group number 2 is going to be Vanessa. Okay, Vanessa, I'll send that to you. Can you please share that with your other group members? And one more group. Share. Anyone with the link, editor. Okay, someone else is John. That's Lizelle. Okay. Use the link, copy the link. And let's see. Who am I going to? Sky is not here, right? Ashley is here. Yep. I'll send that to you, okay, Ashley? And then you share that with the other students. Okay. So here goes. So we are done with assigning the group folder. Keep this link in a safe place. Don't lose it. And let's play a little bit with this link. Make sure everything is working, right? First exercise that I want you to do. Let's make sure lab groups. Here we go. Let us make sure the link is working by doing the following exercises. Okay, 1. Okay. Get a file in your computer. Any file, and rename it with your own name. Okay. Last name plus first initial. Okay. Any file. Okay, after that, click the file, drag, right? Click the file, drag and drop it in your group folder. That's the first exercise. I want to make sure, I want every student in the group to do that. After that, click, the file, drag and drop it in your folder. Can you do that? We're just testing that everything is fine. I don't see there's not any problem. My students, the students who took Physics 6 with me already know how to do that, right? So, do you understand what needs to be done? Let me go one by one here. Let us start with Jacqueline. Hi, Jacqueline, do you know how to do that? Yes, okay. So get any file that you have in your computer, rename it, put your name in the file, and then you click the file, drag and drop into the folder, into your group folder. So far, I don't see any folder there. Now, let's talk to someone in group number 2. Vanessa Escalera, do you know how to do that, Vanessa? It's gonna take some time, right? Yep, I'm trying to do it. Okay, thank you. Now let's see. Let's go back to group. Oh, you did? Okay, so let's see. Yeah, Escalera. Good. So Vanessa did it. Let's see, anybody in group number 1? No, group number 1, not yet. Let's see, group number 3. Sky is not here, right? Ashley, did you manage to do that? Yes, let me check there. Ash, okay. I need the other group members to do the same. Okay, not just Ashley, but just a matter of practicing, right? Corina, can you do that, Corina? And let's see, group number 1. Nobody group number 1 did that yet. Let's see. Let's see. Let's talk with Yorgo. Yorgo, did you manage to do that, Yorgo? Yorgo is here. No, Yorgo is not here. I sent a Canvas message with my contact info and the drive link. Yeah, I don't see Yorgo. Okay. Let me put like half for him. Okay, Lizelle. Did you manage to do that, Lizelle? Please, Lizelle.
I'm having trouble accessing the drive.
You have a hard time accessing the drive?
Yeah.
Your group number. Did you get the link?
No, I accidentally disconnected when I think you sent the link. Sorry.
But you do have the link, right? When you click the link, you don't get to the folder.
I don't think I got the link. I'm sorry.
Okay, gotta get the link first. Ask Alexandra. Alexandra, no, Jacqueline, right? Let's see. Yeah, Jacqueline. This is Vanessa. Let's see, let me help you out. Copy link. Okay. And since we have so few students, I will send the link here. Let's see. Jacqueline already has it. Lizelle doesn't have it, right? I'll send it to you, Lizelle. Don't share this link with anybody outside your group, okay? That's the link. Now you should have the link. And Paul, did you manage to create the file, Paul? Let's see if that. Oh, nobody from group 1.
I just got the link. I'm trying to access it right now.
Okay, good. And what about Jacqueline? Did you manage to? to drop the file there, Jacqueline? I'm working it. Okay, good. So let's see the other group members. Group 2. Okay, group 2 is done, right? Yeah. Group 2 is Vanessa, Norberto Ruben. Okay, Norberto Lopez. Good. Vanessa Mena. Good. So group 2 is done. Yeah. Now, what about group 3? Group 3 still have, well, Sky is not here today, right? He's not here right now. Ashley managed to do that. Now I'm waiting for Corina, right? I'm still working on that. Okay, good. Thank you, Corina. Thank you for the feedback. And going back to group 1. Oh, Jacqueline. Okay, what you did, Jacqueline, you didn't drop the file. You created a folder, okay? That's what you did here. Do you see here? What I want you to do, I want you to get one file, any file that you have there in your computer. Here you go. Let's say I have this file here, my own file, right? I'm going to click, drag, and drop. When I do that, see the file shows up in your folder, right? What you did here was to create a folder. You right click it and then you highlighted new folder. Okay, you didn't transfer the file. You will need this skill to upload your report. Okay, let me delete this guy here. So try to do that, please, and delete. How do I delete it? I'll write in here. And let's see, group 2 is done, right? And now I'm gonna look, actually, okay, group 3 is a little bit behind. Group 1. Okay. Wait. After that, click the file. Okay. Do not create a folder, right? Do not create a folder. Just, click, drag, and drop a file from your computer. Okay. See. Going back to group 3. Any problems there, Corina? Do you need any help? Okay. $737. Sorry, the computer is really slow. Oh, that's so sad when you have computers and problems with computer, right? Yeah. Let's see. Yorgo is here. No, Yorgo is no longer here. Lizelle. Okay. Do you have any problems there, Lizelle? Did you manage to? You should have the link now, right? Because I emailed you the link. Okay, here you go. Lizelle managed to do that. Thank you. Okay. So Lizelle is in good shape. What about Paul? Paul, do you need the link? If you have any problems, I can send you the link.
Yeah, could you just send me the link, please?
Yeah, let me send you the link. And let's see, copy, share, copy link. Paul Zapata, right?
Yes.
Paul Zapata, let's get that. Paul Zapata, don't share this link with anybody. Okay. So now you have the link. Let's see, group 3, Ashley, and that's Corina. Do you have the link, Corina? If you don't have the link, let me know and I'll send the link to you.
I have the link.
Oh, you have the link? Okay. So do you need any help in uploading a file there to your group folder?
I'm just having trouble with the computer itself. It's nothing
Okay.
about
Oh, yeah.
yeah.
Yeah, it's the computer that's slow, right? Yeah, there's nothing much I can do about that. Okay. Okay. Jacqueline managed to do that. That's good, Jacqueline. And let me remove this one so you don't have too much stuff there. And Jacqueline managed to do, Yorgo is not here. Leslie did, and we're waiting for Zapata, right? For Paul to upload his file. Okay, and Yorgo.
I just uploaded something. If you could
Okay, let's see. Let me refresh it here. Yeah, I see it. See that, Paul? Good. So that's a good exercise because you're, like I said, you're gonna need it when you start uploading your files, right? So Jacqueline, I'm gonna keep upload. Jacqueline managed to do that. Yorgo is not here. He's not here. Lisette managed to do that, and Paul Zapata managed to do that. Everybody in group number 2 managed to do that, right? Everybody, Vanessa, Norberto, and the other Vanessa. And then let's see group number 3. Ashley managed to do that. Okay, Corina did that too. Yeah, good. So now,
Professor,
yeah.
Yorgo is saying that his laptop isn't working. And I just sent him the link to our folder so he could upload a file.
Okay, good. Okay, so Yorgos, you said that his laptop is not working. Is that what you said?
Yeah.
Okay. So let's hope he gets. Let's see if he uploaded. Yeah, he didn't upload anything. Okay. Now that everybody managed to upload it, just delete your own file. Okay. I'm not gonna do that, but the way to delete it is click the file, right click the file, and then remove. Okay. Remove it just to make sure everything is working fine. Now that you upload, now that you had all the trouble to upload it, now just, delete your own file. Don't delete someone else's file. Okay, delete just the file that you uploaded. And it's 11:45 right now, so I did everything that I want to do. I just want to make sure that you can delete the file there. Click, right click, and then remove it. Remove the file, right click, and then remove it. Or just click here and click the trash can, right? Lisel, same thing, right? Paul Zapata. So, okay, Corina managed to delete her file. Now it's up to Ashley now. Let's see. Group number 2, we used to have 3 files there on group number 2, right? So who deleted that? It was Vanessa Escalera. Okay, now Vanessa Mena and Ruben and Norberto need to delete their own file. Okay, Norberto did. Now it's Vanessa. Vanessa also, let's see. Let me refresh. Yeah, okay, good. Group number 1. Yeah, okay, just Jacqueline that needs to do that now. Let's see, upload, delete. Okay. Yorgo, okay, I don't see Yorgo there. Lizelle and Paul managed to delete the file, right? Group number 1. No, Paul didn't manage to delete yet.
I deleted mine, Professor.
Did you? Okay, so let me refresh it. Let's see. Yeah, okay, everybody deleted. That's good. Everybody group one deleted. Who is this? Let's see. And then group number two. Yeah, everybody in group number two deleted. One, that's good. And let's see group number three. Yeah, everybody in group number two delete. That's good. So we're done. Okay, we're done with today lab. There's 14 more minutes to go. There's not much time to do it, but to do anything else. But next time, next Wednesday, I'll tell you how to prepare the report, and we will do the first so-called lab in there. Okay. Any questions? Any question you'd like to ask? Okay, if you don't have any questions, let us finish now. We're finishing a little bit earlier, and then we join together again on Monday. Okay, and I see you next week if they don't cancel the course, right? So, and again, if you know any friend of yours, a classmate, an older classmate, a previous classmate, encourage them to add this course, okay? In case they need to take Physics 7. Hope to see you next Monday. Bye-bye.
Professor,
Yeah.
when will be the earliest update you'll get about the class getting canceled?
I'm in touch with my chair. He didn't say anything yet, okay? So
Okay.
most likely, I think if they cancel it, we'll find out Monday. I think we'll find out before Monday, okay? If they cancel.
Okay,
But
thank you.
But so far they didn't say anything.
Okay, thank you.
Okay. I'm not scared. É Philippine. Sim, recebi, mas ainda não recebi. Não baixei. Ok. Você já emitiu a nota fiscal? O Ivan vai emitir a nota fiscal. Tá, aqui. Health. Ok. Dá uma olhadinha nas certidões aí que o Léo enviou. 1, 2, 3, 4, 5, 6, que tem tanto assim? 7, tem uma edição. Nossa, você entende as certidões?
Deixa eu ver se isso espera que eu já vou olhar.
Ok, modelos físicos. Negativo, tudo negativo. Mas eu não entendo essas certidões, né? Você deve entender melhor. Eu. Várias páginas. Legal.